Hello, everyone. Dr. White back again with the second screencast of Chapter 3 on basic probability. We're going to look today at expected value and standard deviation of random variables. First off, expected value. Expected value intuitively is what you expect to get for a random variable in terms of the number on average. So suppose you play that dice game a lot of times. So that's the dice game where if you roll the 6 spot, you win $10. Anything else, you lose $1. So in each play, you're either going to get a 10 or a -1. So if you play it a lot of times, you'll get some 10s and you'll get a lot more -1s. What would happen if you averaged up all of those numbers? That is, took the mean of those numbers. What would that be? Well, it's what it turns out to be is called the expected value of the random variable. The random variable was called y, so we say it's the expected value of y. And the way it's written mathematically is EV for expected value. The parentheses are kind of pronounced of, and then you put the random variable name inside of it. Now, this is not, the expected value, strictly speaking, is one number. It's the average of what you would get if you could somehow play the game, like infinitely many times and then average up the numbers. And that's not really quite possible. But we'll see how you can estimate the expected value by playing a random variable lots and lots of times and averaging up what you get. You'll kind of get closer and closer to a certain number that mathematically is the expected value. So let's actually try this out ourselves. Let's set up that little dice game. What we're going to do is we're going to stick together those two numbers, -1 and 10, using this little C function here. And we're going to call the result y. And we're going to stick together the two probabilities. 5/6 is the chance of getting -1, and 1/6 is the chance of getting the $10. Again, the C function is going to be used to stick the two of them together, and the result's going to be called P dot Y. That's just short for probability of Y in my mind. So let's do that setup. Copying this code, head back to RStudio, get to your console, paste it in, and you get these two things in your global environment. The Y, the possible values of the random variable, -1 and 10. P dot Y is the 5/6, which is about 0.833, and the 1/6, which is about 0.167. If you were to just write one of these into the console, like the Y down here in the console, and just enter that expression, you would see the -1 and the 10 again. If you were to write P dot Y, you would see the 5/6 and the 1/6 down in the console. Next, we're going to actually play the game. Rolling the die and getting your money is just the same as randomly grabbing one of these two numbers, the -1 and the 10, out of that Y list. And this can be done with an R function called sample. Sample randomly grabs out of whatever you put first for your input. So this time it's going to randomly grab something out of Y. When you say size equals 1, you're saying, I only want to grab one thing for now. And next up, and this is actually slightly a typo, that should say a prob instead of P. There's a reason why the code will work though, but I don't like that I have that typo there. This is going to tell you the probability of picking each of the two things out of the Y vector. So it'll tell you there's going to be a 5/6 chance to pick the -1 And it's going to be a 1/6 chance to pick the 10 because you've said that the prob is p dot y. And the replace is true just means that after you pick your thing out, you're going to put it back in again, which isn't going to matter this time because we're only doing it once, but you'll see later that we can do it more times. So let's copy this code and give it a try over in RStudio. But before I run it, I'm just going to go ahead and fix it to say prob is p.y. That's probably going to be fixed by the time you get to look at these slides. And now comes -1. I didn't roll the 6th spot. I rolled one of the other sides. I lost $1. Let me try it again. I did the up arrow command. I did the up arrow, got the command back, pressed enter again, lost $1 again. Up arrow. Hey, I won $10. Up arrow, lost $1. Up arrow, lost $1. So I could keep trying this, and intuitively you'd expect that usually I'd lose $1 and sometimes I'd win $10. And if you try it yourself, probably what you get will vary from what I just got, because R is trying to do this stuff in a random looking way. Now, just to kind of check, just for fun, and probably this is only a matter of the screencast, you won't see this in the slides, but if you did say a P there, it still works. And that's because R can figure out that P is the first letter in prob, and so it was able to figure out what you wanted. But usually it's a good idea to give the whole name of the parameter when you're constructing an input using an R function. So I'll fix that by the time you see the slides. So I hope you've tried it yourself now a few times and you've gotten the idea that usually you're going to get a -1. Sometimes you get a 10. Now, what would happen if you played it a lot? You know? So what if you decided to play the game 10,000 times and just write down what you won and lost each time? Then all you have to do is change your call to sample to say size is 10,000. Now it's pretty important to say replace is true, because you're going to pull out of this vector 10,000 times. When you pull something out, you better put it back for the next time that you pick out. So, you know, I could just like copy and run that command. Oops, wrong RStudio. I could do that. But, you know, it would just like try to print out all 10,000 numbers, and it would say, it would run out of patience. And like right now, it's only set to print out the first 1,000 things it sees in a list. And so it's like omitted another 9,000 numbers there. And so you're not even getting the whole sense of it. You can just kind of look there and see that, yeah, you got a lot of -1s and some 10s as well. So you really need like some place to store all that stuff rather than have it just like go out to the screen and then be lost. And so that's the idea behind using this little assignment operator here to bind the name winnings to the result of such a large number of plays. So let's go ahead and copy this whole thing. Wrong RStudio. Okay, let's run this. And so you don't see anything printed out to the console. That's because what you asked it to do was to set the name winnings that you now see in the global environment here to be the results. And so this is a little numerical list of 10,000 numbers, lots of -1s, and some of them are 10s, and it goes on and on and on. Okay. So, for example, when I did it making these slides, you know, here were the first 20 numbers I got. I want you to make sure to stop and run this code, and you take a look at what you get. So like here, I could go and I could look a bit at what I get. If I say winnings, I'm only going to get the first 1,000. Kind of looks a lot like last time. If I say winnings colon like 1:50, I'd say winnings open brackets 1:50 close brackets. It'll give me the first 50. And so you can look at little bits of your long bunch of numbers in that way. But what I wanted to do was to estimate the expected value of this random variable. And remember, that was supposed to be the average of all the numbers you got. So we need to take the mean of our winnings. Let's do that. Here, I'll see if I can type that into my console just for practice. Mean. Yep. Code completion gives me mean. Winnings. Code completion found that. Run it. So I got 0.9492. Lots of tens, whole lot more minus ones, 10,000 numbers in all, and they averaged up to a little bit less than 1 for me. Your results probably differed a little bit from 0.9492 because you got different random looking results. But probably the difference was not that great from what I got here. When I made the slides, I got 0.7886. I wouldn't be surprised for you to get, something in the high 0.7, something in the, the low to mid 0.9s. I'd be pretty surprised if you got like much more than a 1 or much less than a 0.5. Write to me about that if you do. That would be really interesting. So the number that you get from playing it a lot of times is what you could use to estimate the expected value. It turns out that for simple random variables like the ones that we are working with here, there's actually a way to find the expected value precisely. It's this. You add up, that's that sum sign here, over all the possible values of the random variable. That's the little y down here, stands for possible values. You add up the possible value little y times the probability that the random variable is that value. So in this random variable, there are only two possible values, the -1 and the 10. And so I've got to do -1 times the chance of getting a -1, that's 5, 6. And I got to add to that 10 times the chance of getting a 10. So that's going to be a -5/6 coming from this term right here, this first one, and a 10/6 coming from this second term. 10/6 minus 5/6 is 5/6. That's about 0.83333333 repeating. It is 0.83 repeating. So that's the exact expected value. And that's why I was so sure you would, get around in that range when you tried it 10,000 times. If you try it more times, you're probably going to get closer to the 0.833333 than you did before. I'm going to try it out myself. I'm going to go back, just up arrowing, to the line where we made winnings. And instead of 10,000, I'm going to put 1,000,000, a 1 followed by 6 zeros. And I'm going to run it. And it only takes a moment, but winnings is now this very large numeric vector up here, my global environment, 7.6 megabytes of computer space. Wow. It's 1,000,000 numbers. About 6 of them are 10s, and about 5, 6 of them are -1s. But what do they average up to? Mean of winnings. Run that. 0.83403. That's really close to 0.8333333. You probably, if you try this yourself, are also going to get really close to the 0.83333. The more number of times you play the game and average your results, the closer you probably will get to the 0.83333 repeating, the true expected value. So playing it a lot and averaging is just a way of estimating the expected value. Sometimes there's math formulas you could apply that give you the exact expected value. I just want to stress, again, how much sense it makes that this formula gives you the expected value. Because if you play the game many times, since there is a 5/6 chance of losing the dollar, you expect that -1 about 5/6 of the time. Since there's a 1/6 chance of getting the 6th spot, winning the $10, you expect a 10 about a 6th of the time. So about 5/6 of the times you get a -1, 1/6 of the time you get a 10. What you're doing in this little formula here is what's called a weighted average of the two numbers, -1 and 10. You weight them by how often they're going to occur in the long run. So if you know this approach for finding the expected value exactly, you could use it instead of having to do the simulations like we did with the sample function. You could just use R like a calculator. Just enter this, at the console. Or if you're working in an R Markdown document, enter that in a code chunk. -1 times 5/6 plus 10 times 1/6. And you'll get that 0.8333 repeating. Let's try this again on another random variable. Do you remember the one where you flipped the fair coin 3 times? And you said, we're going to say X is the number of heads we get. Here was the probability distribution. 1/8 chance of getting 0, 3/8 chance of getting 1 head, 3/8 chance of getting 2 heads, 1/8 chance of getting 3 heads. So R, using the formula, says the expected value should be the sum of the possible values times their chance. So 0 times an eighth plus 1 times its probability plus 2 times its probability of 3/8 plus 3 times its probability of 1/8. Add them up and you get 1.5, which totally makes sense when you flip a fair coin. 0, 1, 2, 3, they seem kind of balanced around 1.5. And you can also try it out by simulation. This is a good thing to do even when you know the expected value exactly, because it's really cool to see how it plays out in real life. All you got to do is set up a little vector of the possible values of the random variable, and I'm going to call that thing X. Set up another vector of the probabilities. Make sure you write the probabilities in the same order as the random variables. So the 1/8, then the 3/8, then the 3/8, then the 1/8, because you did 0, 1, 2, 3. And call that something useful. How about P.X for probability of getting the X? And then sample from X a lot of times with your probs being P.X, and make sure to say replace as true. And since you're doing it a lot of times, you really need to store it somewhere, and then you can take the mean of all of those results. Let's give this a try. So I'm going to do these 3 lines first. Oops, wrong RStudio. And so we've got our X, 0, 1, 2, 3. We've got our P.X, 0.125, 0.375, 0.375, 0.125. And we've got our heads, 10,000 long. And like the first time it came out 1 head, then 2 heads, then no heads, then 1 heads, your results will vary. And now at the bottom in the console, I'm going to say mean of heads, 1.4863, really close to 1.5. If I'd done it a million times, I probably would have got a lot closer to 1.5. So you try it too. When I made the slides, I got really close to 1.5. Did you get close to 1.5? I bet you did. Next concept about random variables is standard deviation. You know, random variables have an expected value, and it feels a lot like a sample mean. It's an average. And data also had a standard deviation that was a measure of how spread out the data was from its mean. It stands to reason that random variables might have something like a standard deviation too. In fact, it's so like it that it's called a standard deviation. The standard deviation for a random variable is a give or take figure. You know, the expected value of a random variable gives what it's expected to be on average in the long run. But it's not necessarily likely that the random variable is ever going to be equal to its expected value. Think about that dice game with the 10 and the -1. The expected value is 0.8333. The random variable never came out to be 0.8333. It was always either a 10 or a -1. 0.8333 was just like an average. So the random variable is typically going to differ from its expected value. What would be a good number to say about how much it's liable to differ from its expected value? That's what the standard deviation of a random variable tries to tell you. It tries to tell you how spread out, after accounting for probability, the possible values are of the random variable from their expected value. So the standard deviation for some random variable x is written SD of x. And that's what we'll usually offer as the give or take figure. It has a formal math definition. It's right here. It's the square root of the expected value of another random variable. The random variable x minus its own expected value squared. I mean, x is a random variable. The expected value of x is a number. X minus that number would be another random variable. The square of that would be another random variable, so it would have an expected value, and then you could take the square root of the resulting number, and that's called the standard deviation of x. Now, you're not going to have to memorize this definition. You want to get deeper into things, you learn calculus, and you can take some advanced probability, and you will be using this definition, working with it a lot. What's going to happen for you in this course is that mathematicians are going to come along and they're going to give you easier formulas for the standard deviations of random variables that you meet. They're all based on working mathematically with this definition, but they'll be easier for you to use. But since that's all we've got here for right now, let's see how that formula applies to the very simple random variable that we've been working with, this random variable, with one of the random variables we've been working with. How about the one where you flip a fair coin and you win $12 if it's heads and you lose $10 if it's tails? How about that one? So the distribution of this random variable is, let's see, there's a 50% chance that you're going to get a 12 and another 50% chance of a -10. Now, let's go step by step to find the standard deviation of this random variable. Well, the formula had you finding the expected value of the random variable inside of here. So you're actually going to have to find the expected value of W first. Well, fortunately, it's easy. 50% chance of a 12, so 1/2 times 12, plus 50 chance of the minus 10, so 1/2 times minus 10. So let's see, that is 12 times a half is a 6. Minus 10 times a half is a minus 5. 6 minus 5 is a 1. You would expect to win $1 per game on average if you play this game. Now let's think about how to use this in the formula. The standard deviation of W by definition is the square root of the expected value of the square of W minus this expected value. The expected value of W is 1. So we're really going to be looking for the square root of the expected value of the square of this new random variable W minus 1. So we're going to focus in on this random variable here, W minus 1 squared. So I think about what it could be. Well, there's really only two things that could happen. The W could be 1 or minus 10. So there's a 50% chance that my W minus 1 squared could be 12 minus the 1 squared. And there's a 50% chance that it could be minus 10 minus the 1 squared. Now, 12 minus 1 is 11, and the square of that is 121. Minus 10 minus 1 is a negative 11. Square that, and you also get 121. So half of 121 plus half of 121 is a whole 121. And then you take the square root. So you'd be doing standard deviation of W is the square root of all that stuff. It's the square root of 121. That's 11. So when you play this game, you expect to win about $1 on average each time, give or take $11 or so. That's a big spread because the 12 and the minus 10 are spread way apart from the 1 that you get on average. Now, some random variables have just pretty weird distributions, like the one with the dice, thinking way back to the beginning here. Basically you're going to get a minus 1, but you had a little chance to get something way off of it, a 10. But other random variables, think about that coin flip, they have a distribution that looks more bell-shaped. When you looked at this graphically back earlier in these slides, it was 4 sticks. The 2 on the outside were short, and the 2 on the inside were big, but they were symmetric. When you put all the sticks together, it looked like one hump. So when a random variable ends up looking like that, then the 6895 rule actually applies pretty well to it. When a random variable has a roughly bell-shaped distribution, when the sticks in for the probability follow a roughly bell shapes together, there's going to be about a 68% chance that the random variable is going to turn out to be within 1 standard deviation of its expected value. There's about a 95% chance that it'll turn out to be within 2 standard deviations of its expected value. This is something that we're going to think about more and more as time goes on, but I'll give you a little sense about it before we leave today. Let's think about that coin game again, the one where you win $12 if it's heads, or you lose $10 if it's tails. Suppose you didn't play it once. Suppose you could play it 2,000 times. And you didn't have to pay as you go, but you just collect your net winnings or pay your net loss at the end. So you don't have to have like any money up front to cover you in case you like lose $10 a lot at the beginning. You just like let it go 2,000 times, and then somebody adds up all those 12s and minus 10s, and you either get the money if it's positive or pay that amount if it's negative. Would you want to do that? And also, how much would you expect your net winnings to be? Give or take about how much? Well, this time, you're playing the game 2,000 times, and you're looking at your sum of your winnings. Your net winnings is really the sum of 2,000 12s and minus 10s, all added together. And it turns out, this is math theory, that if you try a random variable x, any old random variable, n times, then the sum of them is another random variable, which will have an expected value. And it turns out it's going to be n times the expected value of the random variable itself. And the sum of your tries is also going to be a random variable that has a standard deviation. And it's going to be the square root of n times the standard deviation of the random variable itself. So in the game here, the expected value for your net winnings, how much you would expect to have total after playing 2,000 times, would be 2,000 times the expected value of W. That's 2,000 times 1, that's $2,000. I would want to play this game 2,000 times because I think I would come out about $2,000 ahead. Give or take some for chance variation in what actually happens. What's the give or take figure? Well, the standard deviation of my sum is supposed to be the square root of 2,000 times the standard deviation of W. Square root of 2,000 times 11. Now, the square root of 2,000 is about 44.7. Times 11 gives you about $492. So the way I'm looking at it is that I would expect to win about $2,000 net, give or take $492 or so. And remember that 6895 rule says that if the distribution of this sum is roughly bell-shaped, then there's about a 68% chance that the random variable is going to turn out within a standard deviation of its expected value. And so if I take the expected value minus the standard deviation, you get 1508. The expected value plus the standard deviation, you get 2492. About 68% of the time, like if I were allowed to play this game 2,000 times every day, about 68% of my days, my net winnings would be somewhere between $15.08 and $24.92. That's what I expect would happen if the distribution for the sum of my 2,000 plays is really about bell-shaped. So let's just see what happens if we play 2,000 times. Well, let's set up our winnings, 12 and minus 10. Probabilities for our winnings, 0.5 and 0.5. And let's sample from our possible winnings 2,000 times, 50% chance for each one. Replace as true. And after we sample, we're just going to sum it right up. So copy this code, head to our studio, paste. And so I got $2,022. It came out $2,022 ahead. When I did the slides, I came out $2,528 ahead. So when I just tried it right now, I came within that 1508 to 2492 range. When I tried it on the slides, it came a little bit outside that range. I'd like you to try it. What'd you get? Did you land inside or outside of this 1 SD range? Okay, so you've tried it. I'd like to just make it a little easier for you to try it again and again without having to copy and run all that code, but also to keep a record of your results. So there's a little function that comes along with the TigerStats package called make game. And what you can do is make one of these, simple discrete random variable coin and dice type games. When you, all you got to do is with your parentheses, when you use the function, you got to give an input that says what are the possible values of the random variable that you're going to play again and again. And that's called outcomes. So for us, they're -10 and 12. And you got to say what are the probabilities for those outcomes. That's 50% either way. And the third input is how many times you're allowed to try that random variable. And then the sum of your wins and losses, the sum of your like -10s and 12s, is going to be what comes out. So we're gonna use this function make game, and it's going to make a little game player for us that plays this game for us any number of times we want. And that game player is called game 2000, because that's what we decided to call it here on the left of that assign sign. So I'm going to copy that, head to RStudio, paste it in and run it. And now I've got my game 2000 in my global environment here. It's a function of a little parameter n, which by default is 1. N is how many times I want to try playing this random variable 2000 times. So I'm going to give this a try. I'm going to say game _ 2000. And I'm just going to try it once. I'm going to say n is 1. Okay. And it says in 2000 plays of that little W random variable, I won 2,396. Let me try it again. I just did an up arrow. And I'm going to run it again. And it says, hey, the next time you played it, you won 2,154. I'm going to move my face out of the way here. Get back to the console, do another up arrow. So I'm going to try it again. In 2,000 plays, you won $2,770. Now, what you didn't know was that it was actually keeping track of all the earlier times you tried this. And once you've tried it 3 times, it starts trying to make a graph of your results over here in the plot window. So here's a density curve for my 3 results so far. The 2154 is this little tick mark I'm waving around with my mouse. The 2396 is this little tick mark. And the 2770 is this little tick mark. And now, every time I up arrow and get the command and play again, so this time I won 2220, it redraws the density curve. And that density curve is trying to show me what net results are more likely and which of them are less likely. So if I just keep on playing it once, I'll add an extra tick mark every time. And I'll gradually build up a density curve that gets more and more stable in its appearance. So I'm just up arrowing and running again. So every time I run an R command over that console, I am playing that 12 minus 10 coin flip game 2,000 times and adding up my results. A lot's happening here. Every time my net winnings is getting stuck onto this rug down here, and a density plot's being made out of it. And what I see forming over here in this plot window is a big hump, somewhere around 2000, a little bit centered off of it. Whoops. I think I accidentally messed myself up. I accidentally created game 2000 again. So I've gone back to, I've kind of lost all my previous results. So I'd like you to try that, okay? Just try making a game and playing it once a lot of times by up arrowing and see what kind of result you get over here in the plot window. Now, I'll point out that you didn't have to call your game Game 2000. Here, I'm going to get that code back where you make the game, but instead of Game 2000, I'm going to call it Peter and run it. There's Peter. It's a function of a variable n. And I'm going to say Peter equal 1. And there he goes. 121.54, 116.04, 126.66, and I'm starting to make a density curve again. Doesn't matter what you call your function, just make that game player function, and then you can gradually build up this density curve. You give that a try. But there's more. When we've been playing the game, we've been trying it the 2,000 times once every time we ran the function. We can get that function to do more work for us. We can get it to play 2,000 times and get the net results as many times as we like by varying the n. So instead of like n equals 1, what if it did n is 2,000? Let me give that a try. So I'm going to go and make my game 2000 again to start from scratch. And then I'm going to try game underscore 2000. N equals 10,000 times. Whoa. So instead of gradually building up the density curve, I've built one right away off of what's like 10,000 people, each one getting to play that 12 minus 10 game 2,000 times and getting their winnings. And you can see that people mostly got around 2,000 bucks. Sometimes they got a lot more, like 3,000 or more bucks, but not very often. There's very little area under the density curve past 3,000. And sometimes they got like less than 1,000 bucks, but not very often. Nobody ever lost money playing this game 2,000 times. Looks like for me, the lowest value was about maybe somewhere around $100, that low tick mark there. That's the lowest net winnings that ever happened for me. If I go up arrow again and run with n equals 10,000 again, I'll add on another 10,000 results. So now that's based on 20,000 people trying this out. And still we have this very kind of bell-shaped situation. So I hope you give that a try too. And let's think about what this means. The individual 10-12 game did not have a bell-shaped distribution. It was just 50% chance of this, 50% chance of that. But playing 2,000 times and adding up the results, has a very bell-shaped distribution. We saw that. So the 68-95 rule for probability works really well here. This diagram here is a density curve for trying it out with 10,000 people. Each one gets to play that game 2,000 times and sum the results. And the blue lines here are at the expected value minus a standard deviation and the expected value plus a standard deviation. And I want you to look at the area of the density curve that's between those two blue lines. That really does look like a majority of the curve. It looks like about 68% of the total area of the curve. These red lines go from the expected value minus 2 standard deviations to the expected value plus 2 standard deviations. And that's definitely most of the curve. In fact, it's about 95% of the area of that density curve is within that range. And so that's how the expected value and the standard deviation for a random variable can work really well together to tell you what's likely to happen for that random variable and what would be unusual for the random variable. The expected value plus 2 of those 492s is 2984. And it would be really unusual for somebody to come out more than $2,984 ahead when they play this W game 2,000 times. The expected value minus 2 of those standard deviations is 1,016. It would also be really unusual for somebody to come out with so little to show for playing that game 2,000 times. 95% of the area is between the two red lines. This curve is symmetric, so I'm figuring 5% outside, about 2.5% chance of getting bigger than 2984, about 2.5% chance of getting less than 1,016. So although an individual W game, win 12, lose 10, could feel kind of risky and not fun, playing it 2,000 times should feel really great because you're probably going to come out around 2,000 ahead. Even if you're really unlucky in your 2,000 plays, you're still coming out pretty far ahead total. See you next time, and we'll look into the DA, where you get the chance to think a little bit more about expected values of random variables.